Hi and welcome to this lesson on gas equilibria and Kp. In our last lesson, we introduced partial pressures and how to calculate them for a mixture of different gases. In this lesson, we're going to be having a look at reversible reactions, equilibriums, dynamic, heterogeneous and homogeneous, and we're also going to be looking at how to calculate Kp and its units. Reversible reactions. So we know that these are reactions that can go in either direction, and many reversible reactions occur in the gaseous phase. And that's what we're going to be looking at in this lesson, those types of reactions. In a closed system, these are all going to be happening in a closed system. What we mean by that is that no product or reactant can leave the reaction vessel. An example of a equilibrium that you will have come across before, most likely, is the Haber process. So here we've got nitrogen and hydrogen forming, so nitrogen and hydrogen forming ammonia. And this is a reversible reaction where all of them are in the gaseous phase. And of course, this isn't balanced. So I need to make sure I'm doing a few things here. Now this is a closed system, and you can see from this box around the outside, it's telling me that no products or reactants can enter or leave. So this system is constantly making ammonia and then reversing back to making nitrogen and hydrogen on a constant basis. The forward and backwards reactions are happening at the same rate. And this is used because we might want to use ammonia for fertilizer and other products. Dynamic equilibrium. It is a closed system reversible reaction, where the rate of the forward reaction is equal to the rate of the backwards reaction. And I like to think of an analogy of someone on a travelator or on an escalator, and they're going up the escalator in the wrong direction. So the escalator's going down, but they are walking up. If they walk up at exactly the same rate that the escalator is traveling down, they're going to hold their position on that escalator. So they're not going to move anywhere, they're going to stay exactly there, but they are still walking forwards, the forward reaction is still going, and the escalator is still moving downwards. And that is a really good representation of what a dynamic equilibrium is like. So it's important to know that the temperature, concentrations, and pressure remain constant at equilibrium. If you change any of those factors, it will change what we call the position of the equilibrium. We have two main different types. A homogeneous equilibrium, which is where the reactants and the products are all in the same physical state. And in this lesson, we're mostly focusing on, well, we are fully focusing on those where we've got a gaseous state. But we might have a homogeneous system where everything's in a gaseous state, or we might have a heterogeneous system where some of the reactants or products are in gaseous and some are in other states. So they're in different physical states. Here is a graphical representation of what this looks like, where we've got the forward and backwards rate happening at the same time. So if we're looking at the Haber process again, so we're taking these, I've got my reversible arrow. Great. And first of all, I'm going to show my reaction rate of my forward reaction. So if I had ammonia, I'm just taking my forward. Of course, there's meant to be a 3 there. There we go. So I'm just considering if I had a system and I just put nitrogen and hydrogen in there and I just let it settle and start to make the ammonia and start to establish that equilibrium, then we're going to have a very fast rate of reaction at the start. Whereas if I reverse this and instead I start with a load of ammonia in a pot and I leave it and it starts to make nitrogen and hydrogen. Of course, there's meant to be a 3 there. Then that's going to be what we call the reverse reaction. And this is, of course, the forward. So at the start, depending on what materials you start with, whether you start with your reactants as such or your products, we're going to have the forward reaction happening very quickly as we use up the excess that we've got. And in terms of the reverse, if I start off with no ammonia, I'm not going to have any rate of reaction going on. But as I start to make it, we start to see the reverse reaction happening, and that starts to pick up pace. Eventually, when we leave the system to equilibrate, we will eventually end up with what we call our equilibrium state, where the forward and reverse reaction are happening at exactly the same rate. Where does Kp come into this? Well, Kp is worked out in a very similar way to Kc, which you've come across before. So Kp is like the equilibrium constant Kc, but it uses partial pressure. So instead of concentrations, Kc, clue in the C, Kp is partial pressures, and we looked in the previous lesson of how to work those out. So the units for Kp are calculated in exactly the same way as Kc. So if I give you a pretend example, and I'm putting their states here as gaseous because that's really, really relevant. So here I've got a system with 2 reactants and 2 products. And my equation for Kp, just like it would be for Kc, is I put my products on the top line and my reactants on the bottom line. But I'm going to write Pe because I'm using a partial pressure. And it's going to be to the power of whatever my, well, stoichiometric number is, okay, in front, just like with Kc. And it's going to be times my partial pressure of F to the power of any molar number that I've got there, divided by A to the power of A times the partial pressure of my gas B to the power of any number that's in front there. You need to use the units for pressure that you were given in the question to work out Kp, and make sure all of your units are the same. In the previous question, or the previous example, we had a homogeneous solution or closed system because they were all in the gaseous phase or state. But we need to know what to do when we've got a heterogeneous equilibria as well. So the expression for Kp for a heterogeneous equilibria would exclude anything or any products or reactants that are not gases. We do not include them in the equation. So for example, if I've got my system here, and these 2 are gases, and this is a solid, then my Kp equation is going to be my partial pressure of my ammonia to the power of nothing, because I don't have a big number there, times my partial pressure of H2S. And again, not to the power of anything because I don't have a stoichiometric number. And I do not include this, okay, because it is a solid. So it's not to be included in the calculation for Kp. Here's a question to have a go at. Pause the video and give it a go yourself, or wait for my worked example. Let's start by writing out an expression for Kp and plugging in my known values. So Kp is going to be the partial pressure of my ammonia to the power of 2, because I've got a 2 here, divided by the partial pressure of my nitrogen to the power of nothing, times the partial pressure of my hydrogen to the power of 3. And then I'm going to plug my known values in. So I know that my partial pressure for my ammonia is 96. It's going to be 96 squared over 16 times 48 cubed. And put that into my calculator, and I'm going to get 0.0052 kilopascals to the minus 2, because I've got kilopascals squared over kilopascals to the power of 4. So 2 of those are going to cancel out, and it's going to leave me with kilopascals to the minus 2. Work out the units in exactly the same way you did for Kc, but instead of moles per decimeter cubed, it's kilopascals, but it's the same skill.